Hey everybody, in today's lesson we're going to take a look at section 3.9, which is all about differentials. So we're starting off with a graph, and you see this curve in here, and that curve we're going to say is our function f of x. So a little function f of x right there. We'll just call it f for now. And notice in here that we have a couple of different lines drawn. Remember that the line that intersects the graph at two places is referred to as the secant line. And the line that intersects the function in just exactly one point is our tangent line. So this line down here is our tangent line. Now, if we take a look on the x-axis at the place where, right directly below our point of intersection is, we're going to label that point, or that x value, with just x. Okay, so we're taking a look on our x-axis. This right here is our y-axis. If we go to the next point on our secant line up here, and we mark that place off on the x-axis, that x value can be found by taking our original x and then adding the change in x to it, so x plus delta x. So this distance in between x and x plus delta x is represented by delta x. That's just the change in the x value. Now remember, when you have an x value, you can evaluate that function, and when you do f of x, that gives you your y value of that point. So y is marked off here on the y-axis, but that could be represented by f of x, because that's the value of your function when you plug in that number x. And that means that up here at this point, we could find that value by doing f of x plus delta x. Okay, so for the secant line, we refer to this distance, this horizontal change, as our delta x. So you can see that right below here. And then this vertical change right here would be referred to as delta y. Okay. So delta y is the difference in y for the secant line. Remember that this comes from the fact that the slope of our secant line is equal to delta y divided by delta x. So we have delta y over here, we have delta x here. All right, now take a look at your tangent line. The slope of the tangent line, remember that that is found by taking the first derivative of your secant. So the slope of the tangent is dy divided by dx. Now, in this case, if you take a look at dx on our graph, it's actually the same as delta x. So delta x is equal to dx. Now, the dy piece, this is the change in y for the tangent line. That's this little piece right over here. So we're going to label that with dy. Okay, so the whole point of doing this exercise is just to make sure we understand the difference between a secant line and a tangent line, and make sure we can find delta y, delta x on a graph, and make sure we can find and label dy and dx on a graph. So just a couple more things, and then we're going to practice two more. Okay, so remember that delta y equals the difference in y for the secant line. And we can express this by saying delta y equals the value of your function at x plus delta x minus the value of your function at f of x. In other words, right over here, this is delta y. Okay, it's the difference between those two y values. And you need to remember this little piece for later. We're going to be finding delta y in a little bit. Okay, since dy since dy divided by dx is equal to f prime of x. Remember, that's our first derivative of our function. We can write, or we have, dy equals f prime of x dx. Okay, so what's happening is we're rewriting that equation so that dy is alone. And that's what's referred to as a differential, okay? So these two formulas or equations are going to come in handy in a little bit, okay? And recall that this dy equals the difference in y for the tangent line. Okay, so let's practice a couple more graphs. Okay, so number one, it says label dx, dy, delta x, and delta y on the graph below. So first of all, it's helpful to identify the secant and the tangent. And I'm going to stick with my color scheme from the previous slide. So this line that goes from this point here to this point right here is going to be our secant line. And I know the other line goes through in 2 points also, but I'm taking a look at the x-axis and I have A and B marked off. So really we're being asked to take a look at this interval from A to B. Okay, so this distance right here from A to B would be represented by delta x, which is the same as dx, okay? So that's our secant line in blue. I'm going to highlight this line right here, and it is our tangent line. I was just about to write line. All right, so this is our tangent. Okay, so if we want to label delta x and delta y, we're going to be looking at the secant line. So come over here, and what you're going to do is just draw a little box. So come down vertically until you reach the place where you can draw a horizontal line over to that other point, okay? So this distance along the x-axis, again, is delta x, which I've got labeled here, and that means that this vertical distance is delta y, okay? If it helps you, you can mark off those two values over here as well, okay? So next, marking off dx and dy for the tangent line. So we already have dx right here. Dx and delta x will be equal to each other. If it helps you, you can draw your second box up above here. And now we're going to come down to our tangent line. Now notice that I'm coming down to the same, I'm working along this same vertical line, and it kind of creates a little rectangle here. So this piece right here is dy, and again, this would be dx. But dx and delta x are always going to be the same. dy and delta y will not be the same, because if they were the same, then the tangent line and the secant line would be the same line. In our next example, it says add a secant line and a tangent line to the curve below for the interval from 1.5 to 4. Okay, the secant and the tangent must both go through x equals 1.5. It's always the first number in the interval where the two meet. All right, so we have 1 and 2, so this is 1.5 right here. So I'm just going to put a point on my graph there. The secant and the tangent both have to go through that point. And the second number in our interval is positive 4 over here. So this right here represents delta x, okay? That's the change in our x value. And we know, again, that that is equal to dx. So those 2 points mentioned in the interval are the 2 points that our secant has to go through. So I think I've been doing a secant in red, so I'm going to come back and just take and draw a line through those 2 points. There's my secant. Okay, and so that means that this right here would be delta x, and this right here would be delta y for my secant line. Okay, for the tangent line, we are going to go through this point, the first number mentioned on the interval, and we are just going to try to touch this graph only in that one point, so it's going to go something like that. Okay, so tangent only touches the graph in one point. It's okay if it goes through later, but we're looking at this point as the point of tangency. And again, I know to use that point because it's the first number listed in the interval. Okay, so looking at dy in this case, we want to go from this point to this point. And I'm choosing this point on the right because it's directly above this point on my secant line. Okay, so this distance right here would be delta y, and sorry, dy for that one. So dy, because we're taking a look at the tangent line, and our dx is going to be the same as our delta x. If it makes it easier for you to see, you can mark these things on the left-hand side as well. So this would be dy, this would be dx. And here we have a case where dy is actually larger than delta y. So our next step is to find a differential, in other words, to find dy algebraically. So it just involves taking a derivative and then adding one more step to it. So for our first example, we have the function y equals 5x squared. So we would take the derivative with respect to x, so dy over dx is equal to 10x. And then you just take and rewrite it as dy is equal to 10x dx, and that's a differential, or dy. So it just involves taking this and rewriting it so that dx is on the other side. So right now we're just worried about the mechanics, like can you actually write a differential, and later on we'll talk about what we do with it in an application. So in our second example, we have y equals sine of x, so we have dy over dx is equal to cosine of x. So dy is equal to cosine x dx. This is an x right here. And finally, in our third example, we have dy over dx is equal to 12x cubed plus 2x. And to write it as a differential, we would say dy equals the quantity of 12x cubed plus 2x, and then we'll leave the dx on the outside of the parentheses, rather than writing it as 12x cubed dx plus 2x dx. It'll be easier to plug numbers in if we just have the dx written once. Okay, so the whole point of finding a differential is to compare dy with delta y. Delta y, remember, is the change in y of the secant line. Dy is the change in y for the tangent line. And we want to see just how close an approximation dy can be for delta y. So in our first example, we have this function y equals x squared. We could write it as f of x equals x squared. That's kind of messy, but you understand that f of x just replaces y. So first we're going to find dy, and then we're actually going to find the value of it when x equals 1 and dx equals 0.01. So we have dy over dx for finding the differential will be equal to 2x. Therefore, dy is equal to 2x dx. So to find the value of dy, again, that's the change in y for the tangent line, I'm going to take 2 times x, which is 1, times dx, which is 0.01. And when you multiply that out, you get dy equals 0.02, 0.02. Now let's take and compare that with delta y. So delta y, if you recall from our previous page of notes, delta y is equal to f of x plus delta x minus f of x. So this time around, you're going to take x plus delta x, which in this case would be f of 1.01, minus f of 1. So you're going to use your calculator, or you can try to do it in your head. You're going to plug in 1.01 where you see x, and then figure out that value, and then go back and do it when x equals 1. So we would have delta y equal to 1.0201 minus 1, and that would give us a value of 0.0201. So dy equals 0.02, delta y is 0.0201, just a little bit more precise because it goes out to a few decimal places, but you see that dy is a pretty good approximation of the value of delta y at that particular point. Okay, so we're going to try another one. It says let y equal x cubed minus 6x. Let x equal 2 and delta x equal 0.1. We have to find dy and delta y. So again, dy over dx, find the derivative. We get 3x squared minus 6. So dy is equal to the quantity of 3x squared minus 6 times dx. So let's plug in our numbers. So dy equals 3 times 2 squared minus 6. That's a 2 there, really. And then dx is 0.1. So 3 times 2 squared, well, 2 squared is 4 times 3 is 12, minus 6 is going to give us 6 times 0.1, which gives us 0.6 for dy. Okay, delta y, we have to find that by doing f of 2.1 minus f of 2. So delta y, if I jump to my calculator, if I plug 2.1 in here for x, everywhere I see an x, we would get negative 3.339 minus f of 2, which happens to be negative 4. But since we're subtracting a negative, that's the same as adding a positive, and we would end up with delta y is equal to 0.661. And again, you can see that dy is a good approximation of delta y. Right, in our third example, we're just going to do part C. Right now it says, let y equal the square root of x, find dy and delta y using the information provided below. So if y equals the square root of x, you can rewrite it as y equals x to the 1/2. So that first derivative, dy over dx, would be equal to 1/2 times x to the negative 1/2, which could be rewritten then as dy over dx equals 1 over 2 square root of x. And dy then, our differential, would be 1 over 2 square root of x dx. Okay, so first we're going to find that dy. Okay, so let's take and plug in those values that we have. So dy would be equal to 1 divided by 2 times the square root of 4 times dx, which is 0.1, or delta x. So dy is equal to 1/4 times 0.1, or dy is equal to 0.025. Okay, for delta y, we would want to do f of 4.1 minus f of 4, and when you take and you plug in those values, we'll get delta y is equal to the square root of 4.1 minus 2, because that would be the square root of 4, which is just 2, and that works out to be delta y equals 0.025 as well. So in this particular case, the two values come out to be exactly the same. Okay, as I mentioned before, today is all about the process, and we'll get into the applications in our lesson on Monday.